Okay, you want to go to page 466. I'm going to write down the data associated with problem number 13.6, actually page 467. 13.6a. So I got a concrete beam similar to that in figure 13.18, sustaining a live load of 1.5 kips per foot. Live load equals 1.5 kips per foot. A dead load equal to 1 kip per foot. I got a cross section on a 24-foot span. Spans 24 feet. I'm using a number 3 stirrup. Number 3 stirrup. Okay. And I've got concrete and steel of 3,040. 3,000 PSI, 40 KSI. And the beam itself has physical dimensions B of 12 and D effective of 26. So I got a beam right here. B of 12 and D of 26. Okay, then there's my bars. Don't need to really worry about. And there's my number 3 stirrup going around in a circle. And we are going to figure out where to put these bars and how far apart the bars will be. So I'm going to calculate a distance for R. And then I'm also going to calculate if S max falls into category A or B. And I'm also going to make sure that the number 3 bar is adequate. So to do this, first thing I need to do is fill those 2 blanks up above that are circled in green. Got to find out the maximum shear in VU. So how do we find out maximum shear? Same way you've always done it. No change. Okay? I've got a beam. The beam is 24 foot long. So what does it make this? The beam's 24 foot long, half the beam must be 12 feet, and 12 feet is 144 inches. I tend to make the dimension in inches rather than feet. Seems to work better. So if I was you, I'd change whatever half the length is into feet, then change it to inches immediately. Okay, so I got a 24-foot beam. It's got 2 loads on it, a live load and a dead load. VU is the reaction, or Vmax is the reaction. So how do you find the reaction? Well, little WU is 1.6 live plus 1.2 dead. So if I take those and I multiply them out, I end up with 1.6 times 1.5. Clear this little sucker. 1.6 times 1.5 gives me 1.6, 2.4. And then I take 1.2 times 1 is 1.2. I add the 2 together, I get 3.6. I go to big WU. Big WU is the total area underneath that factored curve. That looks to be 3.6 times 24. So if I take 3.6 and multiply it by 24, I get 86.4 kips. So if you're following me on your handout, it says multiply, and Vmax is WU over 2. So if I do this, Vmax is equal to 43.2 kips. Okay, let's put him up here. Okay, there's one of the numbers I needed. The other is the other green, VU. Now, hopefully you got similar triangles down. Okay. I'm going to use similar triangle. I'm going to go from here, V max, down to the origin as my height. My width is origin to the end of the triangle. So 43.2 is to 144 as VU is to whatever this dimension is. So if I drop this guy down, put a line here, I need that dimension right there. I need X. If D is 26, that puts this dimension as 26. And if the rest makes up the 144, so if I take 144 and subtract 26 from it, 144, 26 minus, I get 118 for X. So, hopefully this makes sense. 43.2 is to 144 as VU is to 118. So I'll put 118 here. That gives me VU. So if I take 43.2, 43.2 enter 118 times 144 divided 35.4. There's my second number. Okay, on your handout, what we've done right now is we've got ourselves in a position where we figured out letter E, VU. There's the formula. I think the similar triangle should take care of that for you. Okay, now if 5EC is greater than VU, the stirrups are required. If it's less than, excess shear may be present, and we're going to have to worry about that. So right now, we're going to look at calculating V5VC. So I look at my data. VC is 3,000. B is 12. D is 26. I'm using 3,000 pounds, therefore I'm going to get pounds as an answer. All of my other answers are in kips, so I've got to divide it by 1,000. So I'll take it and I'll clear this. I'll say 0.575, 2 times square root. I better do this the other way. 3,000 enter square root. And I'm going to take that and multiply it by 0.75. 2 times 12 times 26 times 2563. So this comes out to 25633. I'm going to move the decimal place back, and this point's going to be 25.63 kips. Now I'm going to divide it by 2, and I get 12.82. So we've just done, on your handout, we've just completed letter F, and then we divided it by 2, and we put the value at the position where R is. So if you go down below, it gives you a little bit more. Letter I is not really required. I would move down to letter K. Okay, it looks like I'm bigger. 35.4 is bigger than 25.63. Therefore, there is a hatched area there. So, looks like we need we need the stirrups. Now what do? Next step is to figure out R. Okay, I'm going to put a little X prime here. And I'm going to use similar triangles again. So if you look at what I'm doing now, I'm going to get rid of this so we've got some working space. I'm going to take similar triangles once again. 43.2 is to 144 as 12.82 is to X prime. So 43.2 is to 144 as 12.82 is to X prime. So if we multiply those, you got X prime. If you subtract X prime from 144, you got where we're going to put them. So let me clear this, and I will take 12.82, 144 times 43.2 divided, and I got 42.73 inches. X prime, 42.73. Let me check that and make sure I'm okay. I don't want to get the wrong data. 43.2, enter, 14, clear. 12.82, enter, 144 times 43.2 divided. That looks good to me. If I subtract that from 144 minus 144, so I got 144, 42.73 minus 102.27. Therefore, R equals 101.27 inches. There's our first requirement. So 102 inches from each end, we're going to have stirrups. Now, our second requirement, is a number 3 bar good enough? Okay, so I'm going to go to letter L. It says letter L indicates that the area steel required is equal to 50 times B, and if you look at B, 12 inches. S max right there says D over 2, 26 over 2 inches, divided by Fy. Fy is 40. Okay? And I would follow the example if I were you guys. It's on page 463. It shows the 40 is really not 40, it's 40,000. So 40,000 PSI. It's going to give me an area. Hopefully that area is less than 2 number 3s. So I'm going to take it. I'm going to clear it. I'm going to put 50 into it. I'm going to multiply it by 12. I'm going to multiply it by 13. And I'm going to divide it by 40,000. 0.195 square inches. Okay, that's how much steel I need. How much do I have? I've got the 2 number 3s. If you go to page 416, you look up a number 3 bar, it's going to tell you the area of 1 number 3 is 0.11. 2 times 0.11 gives me 0.22 square inches. This is what I need. And this is what I have. If I have more than I need, I'm good. So a number 3 will do the job for this particular problem. So I've got 2 of the criteria whipped. I need rebars from each end, 102 1/4 inches, and number 3s are satisfactory. The last is, where do I put them? There's your S max equation. We already went through this. So if I look at my S max equation, it's going to tell me if I need them at 13 inches or do I need them closer than 13 inches. So S max star equals AV. It's either going to be 2 number 3s or 2 number 4s. We just said we're using number 3, so that's 0.22 square inches. On a test, this is a very, very common error right here. A lot of people put in the 0.195. It's not what you think you need, it's what you have. We have 2 number 3s. So 0.22 goes there, FY, 40,000. D, 26 over 5ES. There's 5ES right there. How do I get it? I subtract these 2 numbers. So 5ES is 35.4. 35.4, enter. 25.63 minus 9.77. So you got that? Height between the black line and the blue line is just the values there. Take this, subtract it from that, you should get that distance. So 9.77. Notice that's in KIPS. This is in KSI. We're in good shape. Now I'm going to calculate it. If it's less than 13, I've got to do extra work. If it's bigger than 13, we're going to put them at 13-inch centers. So let's see what it says. It says take 0.22, multiply it by 40, multiply it by 26, and divide it by 9.77. 23.41. So structurally, we could put them almost 24 inches apart. Code says that's not possible. Code says if this number is bigger than D over 2, use D over 2. So use D over 2, and D over 2 is 26 inches divided by 2. So we're going to put them at 13 inches on center. So now I know where they go. First 101.25 inches, that a number 3 is adequate, and that I'm going to put them at 13-inch centers. So what does that look like in real life? Okay, let's take a look at it. Here's my beam. My beam is 24 foot long. I'm going to start putting stirrups in them. And I know those stirrups got to go 101.27 inches minimum. So I start putting them in. The only thing you got to remember is the first stirrup goes half of the minimum distance. So my first stirrup's going to be at 6.5 inches. Then from there, 13, 13, 13, 13. So if I put the next one in, all of these are going to be at 13 inches. That's what I calculated. So if I look at that and I take 101.27